Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to lecture 13 of this course, Flight Dynamics and Aircraft Performance, MATLAB and Simulink Approach. In 1927, a pilot named Charles Lindbergh made a spectacular solo flight over Atlantic Ocean. So at that time, it was never done before, a flight over an Atlantic Ocean. In fact, whole world was watching him. I'm sure in his mind also, he must not be thinking rather about what was the rate of climb, what is the time to climb, and maximum velocity at which the aircraft can travel. So he must be thinking about the maximum distance the aircraft can travel, that is over the ground. So in aerospace terminology, we call it as range. Okay, so let me write here the definition of range. And let me also write here the name of the pilot so that you may remember. So it happened in 1927. Pilot name is Charles Lindbergh. All right, Charles Lindbergh. All right. And what is range? The technical definition. Let me write over here. All right, so this is the total distance that is measured with respect to ground traversed by the aircraft on a tank of fuel, on a given full tank of fuel. All right, the maximum horizontal distance the aircraft can travel when measured with respect to ground on a given full tank of fuel. So here it is actually this range is connected with engine performance. It is connected with the engine performance through a term called as specific fuel consumption. Specific fuel consumption, SFC, we denote it by a small letter C. Okay, do not get confused with the chord. All right, so this is C, this is specific fuel consumption. So this SFC is a technical figure of merit for an engine It is a technical figure of merit for an engine which reflects how efficiently engine is burning the fuel. How efficiently engine is burning the fuel and converting it into power. Alright, so this is related to a specific fuel consumption, that is range. So that is specific fuel consumption is a technical figure of merit for an engine which reflects how efficiently engine is burning the fuel. Okay, remember how efficiently engine is burning the fuel and converting it into the power. For example, let us consider first propeller-driven or reciprocating engine. So let me write definition here. SFC, that is specific fuel consumption, is defined as weight of the fuel consumed per unit power and per unit time. So SFC is defined as weight of the fuel consumed per unit power per unit time. So let me write here SFC equals to weight of fuel consumed divided by power divided by time. Okay. Now mostly engines are rated in terms of horsepower. Okay. So for propeller driven reciprocating engine, mostly rated in terms of horsepower. That is HP. Okay. So I'm writing here C, again specific fuel consumption, equals to weight of fuel consumed divided by the power, that is, let me write here in horsepower, and time. Now mostly students will do mistake here in using the units of specific fuel consumption. Alright. So what do you think the unit of specific fuel consumption will be for this equation or for this definition? Alright. So let us look into the units. Alright. So let me write here C equals to weight of the fuel. We can easily convert it to newtons. Alright. And the power is in horsepower. Let me write here first of all in horsepower. And here time you can convert it to seconds. And what is 1 horsepower? 1 horsepower is 746 watt. And remember, what was 1 watt? 1 watt equals to 1 Newton meters per second. So finally you get 1 horsepower equals to 746 Newton meters per second. So we can write here specific fuel consumption equals to weight, which is in newtons. Horsepower is 746, or let me just rather write here the units, Newton meters per second, and here we have second. So this goes. So yes, the unit is 1 upon meters. Okay, so for propeller driven aircraft, the unit of specific fuel consumption is 1 upon meters. Okay, so do not get any confusion with the units of specific fuel consumption. Now this was for a propeller driven aircraft. Similarly, we can write a definition for jet engines. Okay, so here again the definition will be defined as weight of the fuel consumed per unit. Instead of power, we will write here per unit. Yes, so it will be thrust. Per unit thrust, per unit time. Okay, so here fuel consumption of a jet engine depends upon the thrust produced by the engine. Okay, thrust produced by engine. Okay, whereas for reciprocating engine, it was depending upon horsepower. That is, you can write here brake horsepower as well. BHP. Remember, we discussed about this. It is depending upon brake horsepower. All right. So for jet engines, let me write here instead of SFC, just to do the differentiation between these two engines, let me write here TSFC instead of SFC. All right, equals to weight of the fuel being consumed divided by thrust divided by time. Now, what do you think will be the unit of this TSFC? Can you guess? Okay, so let me write here the designation of TSFC. Instead of C, I am writing here CT. So this means TSFC. All right, so if you see CT, that is thrust specific fuel consumption. CT equals to weight of the fuel. Again, we can easily convert to newtons. Thrust, it is easily in newtons. Time is in seconds. Yes, so the unit of CT is actually 1/second for a jet engine. Okay, so please do not get confused. So specific fuel consumption unit is 1/meters for propeller driven aircraft, and it is 1/second for a jet engine. Now, is there a relation between this C and CT? Can we derive any relation between C and CT? Yes, there is a relation. Let me write here. Relation between C and CT, which we will be rather using. All right. So for reciprocating engine, let me write here, consider for reciprocating engine, C equals to weight of the fuel. Let me write here VWF, F in the subscript, weight of the fuel divided by power in an incremental time. Let me write here dt. Okay. So I can write here WF by dt, you can write here W dot F by power. So what is W dot F? W dot F is the weight flow rate. Weight flow rate of fuel. All right, so this is newtons per second. Okay, weight divided by second. Now from here we can easily find W dot F equals to, that is C into P. W dot F equals to C into P. Now consider for a jet aircraft. Now this was for reciprocating. Now for jet aircraft, okay, let me write here similarly, I can write here CT equals to W dot F. Instead of power, we will get here thrust. All right, obviously we'll get thrust here. So from the above two relations, so from this and this, I can write, or rather let me not write here equation numbers. From these two equations, I can get CT equals to W dot F is C into P divided by T. So let me take this equation as equation number 1. All right. Now we know that power available, we have already discussed, this is equals to efficiency of the propeller into P, where neta is obviously will be less than 1 always. Okay, so power available is neta into P, and we can also mention power available equals to thrust into velocity. Okay, power available thrust into velocity. So we can write here, comparing these two equations, neta p equals to thrust into velocity. So what do we get here? Power equals to thrust into velocity by neta. Okay, now substitute this in 1. Substitute this in equation number 1. So finally we get Ct equals to C upon T. So what is P? That is T into V infinity upon neta. So this goes. So finally we get Ct equals to Cv infinity upon neta. Okay. So this is the relation between thrust specific fuel consumption and specific fuel consumption. That is for both jet engine and piston engine. And let me consider this as equation number 2. So hence it is easy to transform from C to Ct and vice versa, which becomes useful in comparing performance of variety of engines. So because of these reasons, range equations will be different. Range equations will be different for reciprocating and jet engines. Alright, so we are in a way of finding the range equations. So because of these reasons, range equations or range formulas will be different for both, that is reciprocating and jet engines. Alright, so now we will be finding those relations. Okay, so let us begin with the definition of a weight, that is W naught. Consider this W naught as gross weight of the aircraft. So that means here we have fuel load, payload, crew, structures, etc. Okay, so this includes everything, where WF only includes the weight of the fuel. Weight of the fuel, which of course it changes as fuel is consumed during flight. Alright, and W1 indicates weight of the aircraft, when fuel tanks are empty. So at any instant during flight, weight of aircraft W equals to, of course it will be W1 plus WF. Okay, so since weight of the fuel is decreasing, since WF is decreasing at each instant during flight, W is also decreasing. This W, okay? W is also decreasing. I hope you are making notes of this. W is also decreasing. Hence, we can write dW upon dt, change in weight upon time, incremental time, equals to dWf. It is depending upon how much fuel is being consumed in incremental time. So let me write here, that will be W dot F. All right. So here W1 dot will obviously be equals to 0. Also, we can write dW equals to dWf. The change in weight is happening only because of the weight of the fuel is being consumed. All right. So here dW by dt and W dot F are obviously positive or negative. So these are obviously negative numbers, because the fuel is being consumed. That is quite obvious, right? Because fuel is being consumed. All right. Now let us consider a steady level flight. Assume our aircraft is in steady level flight. Considering a steady level flight, where let S be the distance covered, let S be the distance covered over the ground with velocity v. With velocity v. Okay, so I can easily write v infinity equals to ds upon dt. And if interested in finding distance, so ds equals to v infinity dt. All right. So let me just save it. Okay, and let us go ahead. V infinity dt. Okay, now we know that thrust specific fuel consumption Ct equals to thrust specific fuel consumption Ct equals to, that we have already written, minus W dot F. This will be minus, okay, since fuel is obviously being consumed. So d minus W dot F divided by T, and here I can write in this form as well, dWf by dt upon T. Okay, so finally we can write this dt equals to minus dWf divided by Ct into T. Okay, so this Ct goes here in this direction, okay, on the right hand side, and I have taken dt into the left hand side. So dt equals to minus dWf by Ct into T. So next, ds, we have written here ds equals to v infinity into dt. I will simply substitute this dt over here. So v infinity is minus dWf upon Ct into T. All right. Now I can write here minus v infinity upon Ct into T into dWf. I'm just exchanging over here for my convenience. And since we know dWf, because of dWf there is a change in weight, that is equals to dW. All right. So I can write here ds equals to minus v infinity upon Ct into T into dW. Alright. Next we will multiply and divide this equation. Multiply right above equation by W on right hand side. Okay, so let me write here ds equals to minus V infinity upon Ct W by T and dW by W. So for steady level flight, we know lift is equals to weight, right? Please do not forget that. So for steady level flight, we know lift is obviously equals to weight and thrust is equals to drag. Okay, so ds I can write over here minus V infinity upon Ct. So I can write instead of W, I'll write here L, and instead of T, I'll write here D. Okay, and this is dW by W. So remember, we were looking for range, right? So range is obtained by integrating between s equals to 0 to s equals to some distance, say r, okay, where fuel tanks are empty. Where fuel tanks are empty. All right, and W naught, integrating from W naught, that is initial weight, to final weight, that is W1. All right, now writing here 0 to R, ds equals to minus integration from W naught to W1, V infinity upon Ct, L upon D, and dW upon W. Okay, so I've used here for a, that is thrust specific fuel consumption. So I'm talking about a jet aircraft, for example. Now next, I can easily write this equation equals to R. So this is R equals to, I'll flip this integration to remove this minus sign. So this will be W1 to W naught. W1 to W naught, V infinity upon Ct, and this is L upon D, and this is dW upon W. So this equation is general range equation. Okay, general equation, general range equation. Okay, let us take this as equation number 3. So this is for steady level flight. Please do not forget, this is for steady level flight. And also where there is no wind effect. Where there is no wind effect. Okay, so here maximum range of the jet aircraft is provided by the product of V infinity into L by D. So here note here maximum range, you can see here maximum range of jet aircraft is dictated by the product of V infinity into L by D. Okay, so since L by D is also a function of V infinity. Okay, so for steady level flight, we know L equals to W equals to half rho V square SCL I keep on writing the same equation, okay, so that you are well versed with this basic equation. V equals to 2W by rho SCL square root. Now if I see this, the product, that is V into L by D, okay, I will just write here this equation. This is V 2W by rho SCL, and obviously I can write this in terms of L by D. I can also write CL upon CD. These are just the ratios, okay. So this corresponds to 2W by rho S. This goes to CL power 1 by 2 by CD, okay. Let us consider this as equation number 4, okay. So thus product V infinity L by D is maximum when aircraft is flying at CL power 1 by 2 by CD maximum, okay. Now what we'll do is substituting 4 in 3, okay. So this fourth equation we'll substitute in 3. Substituting equation 4 in equation 3, we get, so R equals to W1 to W0, so 1 upon CT square root of 2W by rho S CL power 1 by 2 by CD, and this is dW by W. Now to make things rather simpler, let us assuming CT, density, area and CL power 1 by 2 by CD are constants. Alright, so if we consider this as constant, so these all terms will come outside the integral, okay. This CT 2 by rho S, okay, CL by CD, the W terms will remain inside, alright. So I can write here R equals to 1 upon CT square root of 2 by rho S CL power 1 by 2 by CD, and integral from W1 to W0. So this will be dW by square root of W, alright. So here we have square root of W in the numerator, and denominator we have W, so this reduces to square root of W in the denominator, alright. And if now we can easily do the integration. So when we do the integration, so we get R equals to 1 upon CT square root of 2W by rho S CL power 1 by 2 by CD. So we get here 2 into W0 power 1 by 2 minus W1 1 by 2. Alright, so finally I can write here R equals to 2 upon CT square root of 2 upon rho S CL power 1 by 2 by CD, and this is square root of W0 minus square root of W1. Alright, so this is the final range equation. So let me take this as equation number 5. Alright, now so see here, to get the maximum range, on what parameters it is actually depending upon. So it is depending upon thrust, specific fuel consumption, density, alright, area, aerodynamic ratio, CL by CT, and obviously the weight. So to get maximum range, what we need to do? Obviously, for maximum range, we need to make or fly at CL power 1 by 2 by CD maximum. That is one. Second, for maximum range, we need to fly at lowest possible CT, thrust specific fuel consumption, which was quite obvious, right? We need to consume minimum fuel as much as possible. Okay. Next, it is also depending upon the altitude. So at higher altitudes, your density will be lower and your range will be maximum. Okay. So we have to fly at higher altitudes. Okay. And of course, fourth one is related to the W. So that is carry a lot of fuel. In simple terms, carry lot of fuel. Right. So the third point was fly at higher altitudes. So that's why at higher altitudes range is maximized. That's why commercial jets cruise at above 35,000 feet altitude. Okay. That's why commercial jets or the commercial aircrafts, which are mostly jets, cruise above 35,000 feet altitude. Okay, to get the maximum range, to travel the maximum distance as much as possible. All right. Now we came to know that to fly at the maximum range, we need to fly at CL power 1 by 2 by CD maximum. We have already found the conditions for CL by CD maximum. Similarly, we found the conditions for CL power 3 by 2 by CD maximum. Now, what are the conditions for CL power 1 by 2 by CD? Okay, so that we have not done till now. So let us go ahead and do that. So CL power 1 by 2 by CD. So let me write here CL power 1 by 2 CD naught plus KCL square. Now again, to find out conditions for CL power 1 by 2 by CD maximum, we need to differentiate above equation. Differentiate above equation with respect to CL and equate to 0. Now again, why we are differentiating with respect to CL? Because CD is also a function of CL. Alright, so hence CD naught and K are constants. So since CD is also a function of CL, we are directly differentiating with respect to CL. Okay, now let me write here d by dCl CL power 1 by 2 by CD equals to, the denominator obviously will have CD naught plus KCL square, same method that we did before as well. Alright, so I'm just doing it in front of you so that we get the final results. CD naught plus KCL square into, next we have to differentiate this CL power 1 by 2. So what do we get? 1 by 2 into CL power minus 1 by 2, right? And this, let it be CL power 1 by 2. Now we have to do the differentiation of the denominator. So here we'll get 2KCL. So now this is equals to 0. Alright. So I can write here CD naught to 1 by 2. I'm just multiplying this one with this one. CD naught into 1 by 2 CL power minus 1 by 2 plus K by 2. I'm multiplying this with this. So K by 2 into CL power 2 minus 1 by 2. It is, we have here 3 by 2. Okay. And finally we have here minus 2K CL. The power is 1 by 2. Again we'll have 3 by 2 equals to 0. Okay. Now here we have KCL power 3 by 2. Here we have KCL power 3 by 2. You can consider this as common and then find out or further evaluate this equation. So this is CD naught into CL power minus 1 by 2 upon 2. This remains same, and if you take common, you will get here 1 by 2 minus 2, you will get here minus 3 by 2 k into CL power 3 by 2 equals to 0. So let me write here CD naught into CL power minus 1 by 2 equals to 3k CL power 3 by 2. I just took this term to the right hand side, and in the denominator 2 gets cancelled. So finally I can write here CD naught equals to 3k. So this is power CL power 3 by 2. In the denominator will be minus 1 by 2. So we can write here CL square, 3k CL square. Okay, so your CD naught equals to 3k CL square, that is zero lift drag equals to 3 times the induced drag. Okay, so CL equals to, you can write CD naught upon 3k. CD naught upon 3k. Okay, so this is zero lift drag. This becomes 3 times drag due to lift. Three times drag due to lift. And now finally the velocity we can write here, velocity at which CL power 1 by 2 by CD maximum, that will be square root of 2w upon rho s square root of CD naught by 3k. Okay, so this CD naught equal to 3k CL square. Let us take this as equation number 6, and this is the velocity at which we have zero lift drag equals to 3 times drag due to lift. Consider this as equation number 7. Now finally, can you find what is CL power 1 by 2 by CD maximum? Same way that we did before. So CL power 1 by 2, right? So here CL is CD naught by 3k. So let me write here CD naught by 3k. So this will become, already we have 1 by 2, here we have 1 by 2, so this becomes 1 by 4. Alright, and here CD naught plus KCL square becomes CD naught by 3. Okay, so CD naught by 3. So let me write here CD naught by 3k power 1 by 4 divided by, you get here 4 CD naught by 3. Okay, so I can write here 3 upon 4. So here we have, so 1 upon 3k power is 1 by 4, right? So I'm just writing it separately. 1 upon 3k power is 1 by 4, and then here CD naught power is 1 by 4. The denominator also we have CD naught. So this we can easily write. So 3 by 4 into 1 by 3k. So if I write here CD naught cube, that will be power 1 by 4. Alright, so let me write here. So CL power 1 by 2 by CD maximum equals to 3 by 4. So we have 1 by 3k. If I write here CD naught cube, and this will be 1 upon 4. Alright, so this equation and the previous equation is, we can easily obtain this equation from the previous one. So this is the final relation of CL power 1 by 2 by CD max, and let us consider this as equation number 8. So this is how we obtain the relations for velocity for the maximum range for a jet aircraft. Alright, so for a maximum range we need to fly at CL power 1 by 2 by CD max, lowest possible thrust specific fuel consumption, fly at higher altitudes, carry a lot of fuel. And to fly at CL power 1 by 2 by CD max, you need to fly at this velocity. Okay, So we cannot tell pilot, to get to the maximum range, fly at CL power 1 by 2 by CD max. So we need to tell in terms of magnitude. So to fly at maximum range, fly at this velocity given by equation number 7. Alright. So this was for a jet aircraft. Now similarly, we can follow the same pursuit for a reciprocating engine. Okay. Now let us write equation 3 in terms of C. Okay. So what was equation number 3? Okay. So this was equation 3. So let me write in terms of writing equation number 3. In terms of C, that is instead of thrust specific fuel consumption. Remember, we have already derived the relation between thrust specific fuel consumption and SFC. Alright, so we'll be using that relation. If you really use that equation, or at equation 3, it will become W1 to W0 V infinity upon Ct L upon D dW upon W. You can check this by substituting this. Or rather, let me just do it. I have just rewritten this equation. So from equation 2, so the equation 2 alright, so this was equation number 2, that is for thrust specific fuel consumption, CV by neta. So right here I have Ct equals to CV upon neta. Alright, now I'll write the expression in front of you, that is R equals to integral of W1 to W0 V infinity. So in Ct I will write here CV upon neta into L upon D. So this is dW upon W. So integral W1 to W0. So this is actually also V infinity. So this V infinity goes. So I can write here neta upon C, L upon D, dW upon W. Now again, we will be assuming the similar assumptions, that is assuming flight at constant specific fuel consumption, CL by CD and neta. So these terms will actually come outside the integration. I can write it easily, neta upon C, L upon D, W1 to W0, dW upon W. So neta upon C, L by D. So this becomes ln of W0 by W1. So this is the range equation, that is R equals to neta upon C, L by D, ln of W0 by W1. Consider this as equation number 9. And this is the historical Breguet range equation. Alright, BREGUET, Breguet range equation. So notice here there is no V infinity. There is no V infinity. It is not depending upon the V infinity. Alright. So now what are the conditions for maximum range? So for maximum range, for a propeller driven aircraft, the first thing is we have to fly at L by D maximum. Okay, L by D maximum. Fly at L by D maximum or CL by CD maximum. Second, we have highest possible propeller efficiency. Okay, that is also quite obvious. Have highest possible propeller efficiency. Third is of course have lowest possible SFC, that is C is in the denominator. So this is also quite obvious, that is have lowest possible SFC, that is consume less fuel. Okay, and fourth is of course related to the fuel, carry lot of fuel. Carry lot of fuel. All right. So regarding this first condition, we have discussed at length what are the conditions required to flight L by D maximum. Remember, so for CL by CD maximum, we got the equation, that is 0 lift drag equals to lift due to CD naught. Let me write here, drag 0 lift drag equals to drag due to lift, that is KCL square. Here we get CL equals to CD naught by K. Okay, so this was also the condition for thrust required minimum. Okay, please do not get confused. This was also the condition for thrust required minimum. Okay, now what was the equation? Let me just rewrite here, L by D maximum 1 upon 4K CD naught. All right, and V infinity we can write 2W by rho S square root of CD naught by K. So I've just substituted CL in this equation. Okay, so these are the same equation that we have dealt with multiple times. Okay, now let us do a numerical related to this. So what we are supposed to do is, let us find maximum range for a jet aircraft. So since we are considering jet aircraft since the beginning of this course, we'll find what is the maximum range for this jet aircraft. So here thrust specific fuel consumption must be given, right? So TSFC, that is CT, is given 0.06 kilogram of fuel divided by newtons of thrust into hour. Alright, remember what was the unit of TSFC that we had defined earlier? It was supposed to be per second. Okay, now let us see how can we get this into per second. So let me write here CT equals to, so we will write here 0.06. This is in kgs of fuel. We can easily multiply by 9.81. So you will get now in newtons. And below we already have in newtons of thrust. Hours you can convert it to 3600, and now you will get in seconds. Okay, so if you do this calculation, you will get 1.635 to 10 to the power minus 4. So this will be per second, because this newtons and this newton goes, and finally the dimension will be 1 upon second. Okay, so do not get confused with the units. Most of the students will do mistake here in the units of specific fuel consumption or the thrust specific fuel consumption. Okay, and another parameter given in the numerical is the fuel capacity, which will be required. So fuel capacity equals to 1119 gallons of kerosene. Okay, 1119 gallons of kerosene. So 1 gallon of kerosene weighs approximately 29.68 newtons. Okay, so now we have weight of the fuel, WF, that is 1119 of gallons, and convert it to newtons to multiply by 29.68. So finally you get WF equals to 33,211.92 newtons. So do the calculation by yourself. Okay, do not just blindly follow these numbers. Okay, in this way you'll get a feel of it. And let me rewrite the equation for a maximum range, that is 2 upon Ct square root of 2 upon rho s Cl power 1 by 2 by Cd. Okay, maximum you will get here W0 minus square root of W1. Okay, now here what was W0? W0 was 88,176, which was already given. Okay, newtons. And now we can easily find W1, that is after the fuel is being consumed. So that is total weight, W0 minus WF. So W0 was 88,176.75 minus 33,211.92. So W1 you get 54,964.83 newtons. All right. Now what about Cl power 1 by 2 by Cd maximum? है ना? What about Cl power 1 by 2 by Cd maximum? All right. Now this we can actually calculate analytically as well. So if you see analytical relation, we will do it in MATLAB also, but let us do analytically also. Analytically, so Cl power 1 by 2 by Cd max is actually given as that we actually calculated before, the relation between Cl power 1 by 2 by Cd max equals to 3 by 4 into 1 upon 3k Cd naught cube power 1 upon 4. Okay, and let us substitute the values here. So we get here 3 by 4 into 1 upon 3 into 0.044 0.02 cube power 1 by 4. Okay, so these are given, okay, K and CD naught. So if you calculate it, you will get approximately 23 by 4, 23.4, okay, Cl by power 1 by 2 by Cd. So once you have this, you can easily calculate what is the velocity. Okay, remember velocity at Cl power 1 by 2 by Cd maximum was square root of 2w by rho s square root of Cd naught by 3k. So if you write here 2 into 88,176.75 upon 1.225. So we are finding at sea level. All right, 29.54 into square root of 0.02, 3 into 0.044. If you calculate it, you will get approximately 111.89 meters per second. Now finally we have the Cl power 1 by 2 by Cd max. We have the velocity at which Cl power 1 by 2 Cl power 1 by 2 by Cd is maximum. So we can find what is the maximum range. 2 upon Ct square root of 2 by rho s. So we have Cl power 1 by 2 Cl by Cd maximum, W0 by square root of W0 minus W1. Alright, now you will get you may get confused again about the units of this. All right, so this, of course, this should be in meters, right? Okay, so if we substitute the units here, you will have 1 upon 1 upon second. CT's unit is 1 upon second. 1 upon, we have square root of density is kilogram per meter cube, and this is meter square area. This doesn't have any unit, CL power 1 by 2 by CD, and this is in newtons. Okay, so we can write here this second goes upwards in the numerator, and this, if we solve it, we get meters upon kg. So kilogram meters per second square, so this is square root. Okay, now if you solve this, you will obviously get in meters. Now if you substitute these values, so finally you will get maximum range equals to 4206003.2 meters, which comes approximately 4206 kilometers. Okay, so finally you get maximum range equals to 4206 kilometers. So today we have calculated or found out the relations for maximum range for both jet aircraft and propeller aircraft. Also we dealt with the numerical, where we solved maximum range of around 4000 kilometers analytically. The next class we'll do it in MATLAB. Thank you.